All right, practice test 1, computational questions. All right, the multiple choice speak for themselves. All right, so for 5 points, mean, median, and mode. So you're given a data set. Also follow along while you're doing this practice test with the answer key as well. So when you're watching this video, look at the answer key because I'm looking at the answer key and I'll be explaining everything based on what's on the answer key as well. Okay, so mean, median, and mode for the above data set. All right, so how do we get the mean? We add all the numbers up. You should get 159. And then you divide by the total amount of numbers, right? It's the sum of x divided by n. 159 divided by 12 is 13.5. I'm sorry, 13.25. All right, for the median, you look for the two middle numbers, and the two middle numbers here are 15 and 13, and we do that because it's an even amount of numbers in this data set. Right? If it's an odd amount of numbers, you just take the middle number, but if it's an even amount of numbers, you take the two middle numbers, you add them. So 15 plus 13 equals 28, divided by 2 equals 14. And then you look for the mode, right? The mode is the most frequent number. In this case, 22 is there more than any other number, so 22 is the mode. All right, so the College of Staten Island basketball team faced off against Brooklyn College. The starting 5 players from CSI scored 7, 31, 17, 11, and 9 points. The Brooklyn College starting 5 players scored 2, 21, 13, 17, and 5 points. A Brooklyn College player was injured early on in the game, and a substitute took his place. The substitute scored 14 points. Find the weighted mean, also known as the combined mean, of the n equals 6 Brooklyn College players and the n equals 5 CSI players. All right? So we are adding that score that the substitute scored, and what gives that away is the n equals 6. Okay? And what you do here is you get the sum of x. So all you got to do is get the sum of x1 and the sum of x2. So the sum of x1 will be CSI. So you add up all the CSI scores and you'll get 75. Then you add up all the Brooklyn College scores, including this 14, and you will get 72. All right, now what do? Well, the formula for this is the sum of x1 plus the sum of x2 divided by n1 plus n2. So 75 plus 72 equals 147. 6 plus 5 equals 11. So the weighted mean is 13.36. Next question. The College of Staten Island has been tracking a nuisance deer family. The following data has been collected on the amount of times n equals 6 deer. That should be n equals 7 deer. All right, there's 7 numbers here. It's a typo. Ran into the school library in 2019. The recorded data is 10, 8, 5, 2, 3, 9, and 7. Fill out the table and compute SS, variance, and standard deviation for this sample using the computational formula. Right? You can also use the definitional formula if you want. All you have to do is pull up Chapter 234 worksheet, and I have both of those there. You'll have the tables there, and I might just provide it on the test as well. So I could just provide that on the test for you guys as well, so it's right there on the test. But you also have it as well. So fill out the table. So what you do here is you just plot all the x's. So you got 10, 8, 5, 2, 3, 9, 7. You get the sum of x, which equals 44. Then you square each number. 10 squared is 100, 8 squared is 64, 5 squared is 25, 2 squared is 4, 3 squared is 9, 9 squared is 81, 7 squared is 49. So the sum of x squared is 332. Okay, I remember in class A student said it was 336, and then I put in the numbers and I got 336, which was very weird because then I did it about 15 times again and I got the same number, 332. So I don't know what happened there. That was weird. All right, anyway, so the first step here is you want to solve for sum of squares, right? So for sum of squares, you take the sum of x squared and you subtract it by the sum of x squared, right? So you take the sum of x squared without the parentheses, so that's the second column, the 332 number, and you subtract it by 44 squared divided by n, which is 7. So you do 332 minus 1936, which is 44 squared divided by 7. All right, on this step, I'd recommend you do 1936 divided by 7 first, get that number, and then subtract that number from 332. So you get 1936 divided by 7 equals 276.57. So 332 minus 276.57 equals 55.43. Now, the variance is simply the sum of squares divided by n minus 1. So n minus 1 in this case would be 6. So you do 55.43 divided by 6, and that will give you 9.24. And then to get the standard deviation, you take the square root of 9.24 and you get 3.04. Next question. All right, Z-scores. All right, so for the following population with a mu of 40 and a standard deviation of 7, find the Z-scores for each of the following X values. Okay, so what do we do here? Well, all you're going to do is enter the data into the Z-score formula. Okay, so the Z-score formula is X minus mu divided by standard deviation. So you do 55 minus 40 divided by 7, gives you a Z-score of 2.14 for X of 55. For X of 30, you do 30 minus 40 divided by 7 equals negative 1.43. For the same population, find the score, the X value that corresponds to each of the following Z-scores, okay? So here, you're gonna use the formula X equals Z times standard deviation plus mu. So you're going to do 0.85 times 7 plus 40, which will give you 45.95, and negative 0.45 times 7 plus 40, which will give you 36.85. Okay, for 2. For a population with a mu of 70 and an X score of 62 corresponds to a Z score of negative 2. What is the population standard deviation? So here, what you do is you do the formula for standard deviation for Z-scores, which is standard deviation equals X minus M divided by Z. So you do 62 minus 70, which is negative 8, divided by 2. Negative divided by negative is a positive, so it's a positive 4. Number 3. A distribution of exam scores has a mean of 80, or a mu of 80. If your score is 86, which standard deviation will give you a better grade? A standard deviation of 4 or a standard deviation of 8? So what you do here is you plug in both standard deviations into two separate Z-scores, right? So you're going to do 86 minus 80 divided by 4 equals 1.5. And 86, I'm sorry, did I say divided? 86 minus 80 divided by 4 equals 1.5. And 86 minus 80 divided by 8 equals 0.75. What is a better score here? Well, the z-score of 1.5 is a better score. So for that reason, the standard deviation of 4 is the answer. Standard deviation of 4 will give you a better grade. All right, for the next question. If your score is 74, which standard deviation will give you a better grade? 4 or 8? So now you do 74 minus 80 divided by 4, and that equals negative 1.5. And 74 minus 80 divided by 8 equals negative 0.75. So even though the negative 1.5 is larger, that just means it's further to the left of the mean, which means it's a worse score. So a negative 0.75 z-score is a better score. So then the answer would be a standard deviation of 8. Okay. A distribution with a mean of 62 and standard deviation of 8 is transformed into a standard distribution with a mu of 100 and a standard deviation of 20. Find the new standardized score for each of the following values from the original population. All right, so what you do here is, first, you get the z-score for each x value using the original data before it's transformed. So you do 60 minus 62 divided by 8 equals 0.25. So now what you do is you take that negative 0.25 times the new standard deviation, which is 20, plus the new mean, which is 100, and you'll get 95. For B, you do 54 minus 62 divided by 8 equals negative 1. And then you do negative 1 times 20 plus 100, and that will give you 80. For C, you do 72 minus 62 divided by 8 equals 10 divided by 8, which equals 1.25. So now you do 1.25 times 20 plus 100, which will give you 125. And for D, you do 66 minus 62 divided by 8 equals 0.5. 0.5 times 20 plus 100 equals 110. Next question. Find each of the following probabilities for a normal distribution. So we have Z is greater than 0.20. Z is greater than negative 0.74. Z is less than 1.25. And Z is less than negative 1.27. All right, so greater than 0.20. Now, it's greater than a positive z-score. So you're going to always look in the tail if it's greater than a positive z-score. So you just go to 0.20, look in the tail, and get 0.4207. Greater than negative 0.74. If it's greater than a negative z-score, you always look in the body, and that comes out to 0.7704. Less than positive 1.25. So if it's less than a positive z-score, you always look in the body, and that will give you 0.8944. And if it's less than negative 1.27, if it's less than a negative, you're always going to look in the tail, and that is 0.1020. What proportion of a normal distribution is located between each of the following z-score boundaries? So we have a negative 0.4 and a positive 0.4. So when you have opposite signs and you're looking for the boundaries, basically the two z-scores that separate the proportion in the distribution that separates those two z-scores, you go to column D, which is the column that tells you between mean and z, and you add. So in this case, it's 0.4, negative 0.4 and 0.4. So we know since it's a normal distribution, there is no negatives on a z table. You just go to 0.4 because it will be the same distance. Column D is 0.1554 plus 0.1554 equals 0.3108. B, z is negative 0.9 and z is positive 0.8, right? So you have opposite signs, so you know you're going to add them. So you go to 0.9, column D, and you will get 0.3159. Then you go to 0.8, column D, and you will get 0.2881. The answer comes out to 0.604. All right, I know I mentioned in class it should always be the 4 decimal places over, but if the last place is a 0, you will not lose points for not putting a 0 there. All right, but if it's not a 0, you should always keep it to 4 places. But in this case, you see in the answer key, it's 0.604. That will be acceptable. 0.6040 will also be acceptable. C, a negative 1.5 and a negative 2.5. All right, so they're both falling on the same side of the distribution. So we know we have to take the smaller proportion value of column D and subtract it from the larger, right? So the larger z-score will have the larger, and the smaller z-score will have the smaller. So with that said, when you go, you're going to take 0.4938 minus 0.4332. 0.4938 corresponds to negative 2.5, and 0.4332 corresponds to negative 1.5. When you do the subtraction, you get 0.0606. Now you have a 2.1 and a 3.1. They both fall on the positive side, so the same rule applies. So you go and look up both the proportions, and you'll see for 3.1, it's 0.4990 minus, for 2.1, it's 0.4821. When you subtract those two numbers, you will get 0.0169. Moving along. 3, find the z-scores location of a vertical line that separates a normal distribution as described in each of the following. So 20% in the tail on the left. So what you do here is you go to the tail column, you look for the number that is closest to 20% in decimal form, which will be 0.2000, and you get that proportion, you get that z-score. Now that z-score is 0.84, but if it's 20% in the tail on the left-hand side, you know that z-score must be negative, so it's negative 0.84. Now it says 30% in the tail on the right, same thing, 0.3000. You look for the z-score that is closest to that in the tail column, and if it tells you it's on the right, you know it's going to be a positive z-score, and that is a positive 0.52. 65% in the body on the left. All right, so if 65% of the body is on the left, then you know it must fall on the positive side. So you know it's going to be a positive z-score. And now you just look for what number is closest to 0.6500 in the body column, and that is a z-score of 0.39, and keep it positive. So positive 0.39. 97% in the body on the right. So if 97% of the body is on the right, that means that this z-score is falling on the left. So you know it's going to be a negative. So you look for which z-score is closest to 0.9700, which is the proportion of 97%. And that comes out to a z-score of 1.88. And since 97% of the body is on the right, it will be a negative 1.88. IQ test scores are standardized to produce a normal distribution with a mean of 100 and a standard deviation of 15. Find the proportion of the population in each of the following IQ categories. So genius or near genius have IQs greater than 140. So what do you do here? You just plug it in. So 140 is going to be the X value in your z-score formula. So you're going to do 140 minus 100 divided by 15 equals 2.67. Now, if we're looking greater than a positive z-score, we know we look in the tail. So you go to the tail for 2.67, and that comes out to 0.0038. Very superior intelligence, IQ between 120 and 140. Well, right away, 120 and 140 both fall above the mean, so the z-scores are going to fall on the same side. Using the same method we did before, a few questions ago, when we were looking for the distance between two z-scores, we get the z-scores for both 120 and 140. So you do 120 minus 100 divided by 15 equals 1.33. Then you do 140 minus 100 divided by 15 equals 2.67. Okay, you got to subtract the smaller one from the larger one. So go find the larger one first. 2.67 in column D is 0.4962, and 1.33 in column D is 0.4082, and that answer will come out to 0.088 or 0.0880. All right, average or normal intelligence, IQ between 90 and 109. Right? You see 90 is below the mean, 109 is above the mean. You know the z-score for 90 is going to be negative, and the z-score for 109 is going to be positive. So you do 90 minus 100 divided by 15, and that equals negative 10. Divided by 15 equals negative 0.67. Now you take 109 minus 100 divided by 15. That equals 9 divided by 15, which equals 0.60. Now you go get the two proportions for in column D, and you are going to add 0.2486 for 0.67 plus 0.2257, and that will give you 0.4743. All right, SAT scores. So the distribution of scores on the SAT is approximately normal with a mean of 500 and a standard deviation of 100. For the population of students who have taken the SAT, what proportion have scores greater than 700? 700 is above the mean. We're asking greater than, so we know that we're going to be looking in the tail. 700 minus 500 divided by 100 equals 2. So you go to z-score of 2. Look in the tail, it's 0.0228. What proportion have SAT scores greater than 550? So plug it into the z-score formula. 550 minus the mean, which is 500, divided by the standard deviation, which is 100, comes out to 50 divided by 100, which equals 0.5. So 550 is above the mean, the z-score is positive, so we know we are going to look in the tail. So when you go and look in the tail of 0.5, you get 0.3085. Okay, finding a score, what is the minimum SAT score needed to be in the highest 10% of the population? Okay, so the highest 10% of the population is on what side? It's on the right side of the distribution, right? So you're going to look for 10%, what number is closest to 10% in the tail, or 0.1000 in the tail. And when you go to your table and you look in the tail column, you will see that the z-score of 1.28 is closest to 10% in the tail. So we do 1 point now. Now it wants to know what the score is. So we use the formula to find x from z-scores, right? Which is z times standard deviation plus mean. So it's 1.28 times 100 plus 500 equals 628. D, if the state college only accepts students from the top 60% of the SAT distribution, what is the minimum SAT score needed to be accepted? So if you're in the top 60%, you know that that z-score is going to be negative because it falls below the 50% mark, which is a z-score of 0. So what you do here is you look for 60% in the body, right? Because that's more of a distribution, right? 60% is the body, right? If you go backwards to 40%, in this case, at that point, the 40% would be the tail. So z of the top 60% equals negative 0.25, right? If you look for body and you look for the closest number to 0.6000 in the body, it will be 0.25, and you know it's on the left side because it's a whole 60%, so it's negative 0.25. Now you do the x formula, which is 0.25, which is the z, times 100, which is the standard deviation, plus 500, and that equals 475. Okay, find the z-score boundaries that separate a normal distributions and described in each of the following. So the middle 20%. So if we're looking for the middle 20%, right, the rule is we have to cut that 20% in half to 10% and look in column D for the closest number that's the 10%. So if you do that, you will see that that number is 0.25. So plus and minus 0.25 are the z-score boundaries that separate the middle 20% of the distribution. You split 50% in half, so you're looking for 25% or 0.2500 in column D. And when you look, you'll see the closest number is 0.67. So you do plus minus 0.67, and that's the boundaries that separates the middle 50% of a distribution. The middle 95%, you cut it in half, and you look for what z-score corresponds to that number, and you go and you'll see that 1.96 is the closest. So plus minus 1.96 equals the z-score boundaries that separates the middle 95%. I am looking at the answer key. I see it says 0.196. It's 1.96. It's not 0.196. All right, just a typo. All right, so the middle 90%, what's 90 divided by 2, right? It's 45. So you're gonna look for the column D score that's closest to 0.4500 or 45%. You'll see that that equals 1.64 or 1.65, right? So this is one that won't be on the test, so I'm not gonna have you have one where it's one distance or another. So 1.64 would technically be the better answer because you don't want to overestimate. It's always better to underestimate. But since 1.64, 1.65, let's say it happens to be on the test, I'll accept either answer. But the best answer would be what's in the middle of those two numbers, right? And that's 1.6450, right? But don't worry about that in the test, but it's just good to know that, just to understand the concept behind it. All right, up to the part of the test with our final lesson from chapter 7. So remember, now we're going to use all the other formulas for the z-scores with sample means and standard error. Okay? 5 of these types of questions will be on the test, worth 5 points each. So if random samples, each with n equals 36 scores are selected from a normal population with a mu of 80 and a standard deviation of 18, how much difference on average should there be between a sample mean and population mean? So when you see that, how much different on average should be between a sample mean and a population mean, that's another way to describe what the standard error would be. So you just plug it into the standard error formula, right? So you're gonna take the formula of OM, right? And that is going to be the standard deviation divided by the square root of n. So 18 divided by the square root of 36. So 18 divided by 6 equals 3. A sample of n equals 9 scores has a standard error of 6. What is the standard deviation of the population from which this sample was obtained? So to find the standard deviation, you simply do standard error times n. So you do 6 times 3, and that will equal 18. A sample obtained from a population with a standard deviation of 12 has a standard error of 2. How many scores are in this sample? Right? So we are going to use the formula for n, which is standard deviation divided by standard error squared. So you do 12 divided by 2, which is 6, squared equals 36. So n would equal 36 from that population. A sample of n equals 4 scores has a standard error of 10 points. For the same population, what is the standard error for a sample of n equals 16 scores, right? So we want to find the standard deviation first of that original population. Well, it's coming from the same population. We're finding it for the original 4 scores. Okay, so that would be 10 times the square root of n, which is 2. So 10 times 2 equals 20. Then you are going to take that 20 and divide it by the square root of the new n, right? That's the standard error formula. So you take the standard deviation, right? That's also the denominator in the z-score for sample means. So again, you're taking 20 divided by the square root of 16. 20 divided by 4 equals 5. So the standard error for the sample of n 16 scores equals 5. Right? And you could see, right, another rule is the higher n, the lower standard error. Right? You can see when there was 4 scores, the standard error was 10, and when there was 16 scores, the standard error was half of that. So again, that's just a logical point, and will be asked on one of the multiple choice questions, possibly. A random sample of n equals 4 scores is obtained from a population with a mean of 80 and a standard deviation of 10. If the sample mean is 90, what is the z-score for the sample mean? Now, all we do here is plug it into that new z-score formula for sample means. So we take the sample mean, which is 75, minus 80, and then divide it by standard error, right? OM. And what's the formula for that? You take the standard deviation divided by the square root of n, and n is 25. So square root of 25 is 5, right? 10 divided by 5 is 2. So negative 5 divided by 2, z equals negative 2.5. I'm sorry, I just did number 6, so I'm going to redo number 5. A random sample of n equals 4 scores obtained from a population with a mean of 80 and standard deviation of 10. If the sample mean is 90, what is the z-score for the sample mean? All right, so this is just asking for the z-score, doing the same thing I just said. Take a mean of 90 minus the mu of 80, so 90 minus 80 equals 10. And then you take the standard deviation, which is 10, divided by the square root of n. Right? In this case, n is 4, so the square root of 4 is 2. So 10 divided by 2 is 5, and 10 divided by 5 is 2. So for 5, the z-score is 2. All right. For a normal population with a mean of 80 and a standard deviation of 10, what is the probability of obtaining a sample mean greater than m equals 75 for a sample of n equals 25 scores? So the first thing you do here is you get the z-score. So we're going to do 75 minus 80 divided by 10 over the square root of 25. 75 minus 80 is negative 5, divided by 10 divided by 5, which is 2. So negative 5 divided by 2 equals negative 2.5. Now we want to know the probability of scoring greater than, right? It's a negative z-score. The mean is below the population mean. So whenever we're looking for greater than a negative number, we're always looking in the body. So you go to you go to 2.5 and you look in the body and you will see that's 0.9938. That means that 99.38% of people scored higher than a 75 for that sample of 25 scores. All right, do this worksheet over and over and over. The test will very much reflect this worksheet. I just gave you a step-by-step guide to it. The multiple choice questions, I think most of the class, if not all, in the first class and the second class really understood that information. So I'm not gonna go over that on this review. Just, study the worksheets, study the multiple choice questions that are in this test and the concepts behind it, and just know them, right? Know nominal, ordinal, all the different ways of measurement, interval ratio, right? Population parameter, sample statistic, and also know those things that we learned in chapter 7. And you should be fine. Just look at the questions. Any of the information in this practice test questions, those are the things I want you to focus on. So I know it's 4th of July weekend, but hopefully everybody studies. We will have a review Monday, all right? So I will release the test Monday. At some point Monday, I'll release the test. However, those of you who have questions or want to come to the review, I would say everybody come just to really get it in so you could, do your best. But if you feel good and want to go take it, you're not obligated to come. But for those of you who are going through this practice test and get stuck somewhere and have a question, or you want to debate that maybe I got something wrong, either one, show up 6:30 Monday, and we'll have a full review, and then the test will be released, and you'll have 5 days to complete the test. Once the test is started, you cannot finish the test, okay? You'll be given 4 hours to complete the test, and that's about it. So I'll be making an announcement on Blackboard now. And enjoy your 4th of July weekend. And I will see you guys Monday.